Hello and welcome back to Calculus 3, section 13.7. Yeah, let's open the gates of hell, I guess. What are we doing? We're doing U sub in 2D and 3D. Now, used to be called U sub in one dimension because we used to change the variable x into variable u. With that, we did the transformation of space where x-axis becomes u-axis. And we know that in the integral, we change the limits, we change the function, we change the dx into du, and all of that had the substitution part, and we had to work hard to get that thing to work. And that's outlined, as you can see over here. I did that last class, and we transformed the space. I also did an example where I show how the limits that used to be x1, x2, which are 0 and 2, change into limits 0, 4, which are u1 and u2, and then we compute the problem. Now, you can also compute the entire problem in terms of variable u, and then go back into variable x, and then compute with all limits, but that's just extra work of converting it back. And then we started with the 2D conversions. So now we have to convert our integral, double integral of f of x, y, dA into a different type of an integral that will be in terms of u and v. So there will be a transformation given between the two spaces, transformation which is transforming x into uv and transforming y into uv, and those could be uncoupled or coupled, and we'll see what it is. Now, important part for these transformations is to know that the region changes. So when we do transformations, i.e. uv substitution or whatever you want to call it, your limits of integration will change, and when those guys change, what happens is your region is different. So we use the limits of our double integral to draw the region R, and then we have to transform that region into the new region that will be a region for integral in terms of u and v. Now, transforming to the regions, you have a region. That region, in this particular case, region has 4 sides, and we transformed each one of the 4 sides into this 1 star, 2 star, 3 star, and 4 star. And when we draw what we get from those 4, we see that this parallelogram that was in x and a y is now a beautiful, simple little square in uv. Now, this means that you can set up your integral now, and your function will be in terms of uv, and there will be more stuff there. But your limits now become this. And before, they used to have these things in limits. So much easier to deal with the problem when you are able to transform something that was not a rectangular region into a rectangular region, or something that was not polar into an easy polar region. So let's transform one more region or 2 more regions to see the way this works one more time, or 2 more times, and then move on to actually doing this. Now, these problems are going to be more like 4-step problems. First part would be transforming the region. Second part would be working with Jacobian and substitution. The third part would be actually assembling the integral back together. And then fourth part is to solve the new integral, which has the equivalent solution. So let's transform another region From problem 29, again, I'm not doing the entire problems here, I'm just transforming regions. Region is given by, xy, such that 0 less equal than x less equal than 2. And then we have negative x over 2 less equal than y less equal than 1 minus x. And they're giving us transformation, so we should use transformation x equals 2u and y equals v minus u. So that's our transformation. All right, great. I asked you many times to draw the picture first and then start doing stuff. Because without drawing the picture, you don't really know all of the sides that you need to transform. So we are going to zoom onto this over here. We have the equation y equals negative x over 2. And then over here, we have equation y equals negative x plus 1. So when I to graph, use y equals negative x over 2, y equals negative x plus 1, and x that it's stuck between 0 and 2. So these are the specs that we have to use to graph. Alright, so I'm going to use 2 units as 1, so we can see this better. And now I have the first part, which is y equals negative x over 2, that's at 0. And then we go 1 unit down, 2 units over, so it's right here. 1 unit down, 2 units over, it's here. So I'm going to, or 1 unit up, 2 units over. So I have one of these lines. Then I have positive 1, and then negative x, that's a 45 degrees. And then I have 0 to 2, so my region is this triangle. Now hopefully it's clear the triangle has 3 sides. Previous example had 4. So we are going to use 3 sides. We are going to have 1, 2, 3 sides. Now we have to mathematically describe 1. 1 is on this y equals negative x plus 1 line. And it's stuck, x is stuck between 0 and 2. Number 2. Number 2 is x equals 0, it's a vertical line, and y is stuck between 0 and 1. And number 3 is the other line, which is y equals negative x over 2, and x is stuck between 0 and 2 again.
I have a question for number 2.
X equals 0, so that's the y-axis.
Why we chose x instead of y?
Because y functions are horizontal lines. In the coordinate system, if I draw this is y equals 1, and in the coordinate system, if I draw this is x equals 1. So this line over here that bounds the triangle is a vertical line.
Oh, okay.
So it has to be x equals 0 because it's x-axis. And we are going to use transformation x equals 2u, and y equal v minus u. So now, 1 star. What do I have? Well, let's start with x. We have 0, less equal than 2u, less equal than 2. So we see that 0 less equal than u less equal than 1. That's that. And then I have y and x. So now what's y? Y is v minus u. And what's x? X is 2u, so negative 2u plus 1. You can solve this for v. So v is equal to negative u plus 1. So over here I have my first pair. As you can see, everything is in uv, and that's the new space. 2. We start with x equals 0. So if x equals 0, then 2u is equal to 0. From where u is equal to 0. And we have 0 less equal than, and x y is given as v minus u. And that should be less equal than 1. Now we already have that u is equal to 0 from over here. So we just get 0 less equal than v less equal than 1. And this gives us the second transformation. Third transformation is going to be, again, y is v minus u, is equal to negative 2u divided by 2. Algebra. So 2v minus 2u is equal to negative 2u. And when you put these together, 2u goes to the right and cancels. So you get 2v equals 0. So v equals 0. And we also have the same 0 less than x less than 2. 0 less than x less than 2. So 0 less than equal than x, which is 2u, less than equal than 2. When you divide by 2, no coughing, is 0 less than u less equal than 1. So 0 less equal than u less equal than 1. So now I want to graph this. So now this is UV region, and if I have a UV region, I am able to set up du dv integrals. So we are transforming these things, right? So what do I have? Yes.
How do you decide whether v or u is?
U is at the x-axis. Yes. Mm-hmm. It has been decided for me. Convention. So now we are going to go to the first equation and see that positive 1 and then negative u, and this is all we have, this triangle here. So now you can go and you can set up your triple integral f of uv blah blah blah. So I mean your double integral. So that was a transformation, problem 29. Cool. So your goal is to come up with a list of sides, describe each of the sides in mathematical terms, and then use the transformation given to to change all of those into new one, and we see that we have a much nicer triangle to integrate over than when we started. Because this one, if you are using dx, you have two linear functions in limits, where the one on the bottom has only 0 to a linear function. So it's easier to compute. And that's that. Let's see if we can find another one, maybe something polar. If they have. I don't have a big selection. I don't know, let's see what we can get out of 30, which is the next problem. So, region R is given as set of all points such that 9x squared plus 4y squared is equal to 36. And we want to use x equals 2u and y equals 3v. What is the shape that we have up there? I'm sorry? Ellipse. Very good. It's an ellipse. Have you ever heard of an elliptical integral? No. You know why? It's PhD stuff. That's why. So it's a PhD concept you study as a second year PhD student. Your course is on elliptical integrals. Right there. So what we are going to do is we are going to change this monstrosity into something simple, hopefully, using the transformation. Otherwise we are doomed. All right? So we start from the fact that our coefficients of 9 and 4 are not included in these squares. So I am going to take this equation and rewrite it as 3x everything squared plus 2y everything squared is equal to 36. $20 of gas right there. It's to get from light 1 to light 2 and then stop on the red again. What's the point? Anyway. So now, really, this is a transformation like this? Why? Just want to make sure that I copied it right. X equals 2u. Can you give us a transformation u equals 3x actually? Wouldn't that be more common sense? And you change this into a circle and then polar coordinates are a joke? Do you see that? Let's play it the way the book has it. Maybe there is merit, okay? So I am not going to do this anymore, because to me it was clear that I just include those and I swap everything and I just get u squared plus v squared equals 36. It's a circle, polar coordinates, yay, right? But let's see what we get if we use what they have. So what they have is 9, and instead of x squared, I have to put 2u in parentheses squared plus 4 3v squared equals to 36. Oh, this is going to work too. Okay, good. So we have 9 times 4, that's 36. Okay, there. Okay, I was wrong. Theirs is better. 9 times 4 is another 36. Okay, they win. I lose. Because they have a unit circle, and mine was radius 6. So, all right. I lose this round. Fine. Okay. Oh, by the way, we're done. Because look at your region. It's a unit circle, right? This is a unit circle in UV. Your radius is 1. And if you need your polar integral of f of, r theta, which came from UV, you have your 0 to 2 pi and your 0 to 1. So, yeah. This is good stuff. Nice. What have we done? What part of our basic U sub problem from Calculus 1 have we done so far with transforming these regions? What we have done is we learned how to change these limits into these limits using this and that. That's all we did. Okay? Now, what else is the feature of all of this? It is us figuring out this part where we have to change the derivative portion. And that is going to be done by something that is called Jacobian. Jacobian is a matrix. It's a determinant of the matrix of partial derivatives. And the order of the Jacobian will depend on the order of the problem. So you have 2 by 2 Jacobian of partial derivatives if you are in 2D, and 3 by 3 for 3D, and you know how to compute these determinants. If you go to 4D, 5D, 17D, your matrix will be 17 by 17, and then, good luck. It's life-altering event. Meaning you compute that, and there's no more life after that, because you used it all to compute the Jacobian. That was 17 by 17. So, Jacobian. J of UV is going to be the determinant, so you have this, like absolute value. Dx, du, dx, dv, dy, du, dy, dv. These are all partial. So you get to compute the Jacobian. Now, where are you computing Jacobian from? Well, from your transformation. So input is the transformation. So if I want to compute the Jacobian, let's do just one example. Even that is too much. Like 26. They give you transformation u equals x plus 4y, and v equals 3x plus 2y. Right? So now we need to figure out the Jacobian. Now, I hope you already see the issue in the way the problem is presented. Jacobian is clearly asking you to compute x as a function of uv. which is the way we used to have, see, x and y in terms of uv. Now you have u and v in terms of x and y. So they just try to make this more confusing and more annoying for y'all. We actually have to solve the system of equations and fish out x and a y to be able to do this. So let's do that. We can achieve this by simply doing the substitution method. From the first equation, x is equal to u minus 4y, and I'm going to plug that in here and obtain that v is equal to 3x, so that's going to be 3 times u minus 4y plus 2y. So v is equal to 3u minus 12y plus 2y is 10y. And you can see that from here I am able to solve for 10y. So 10y is equal to 3u minus v, from where y alone is 3/10 u minus 1/10 over v. You see that this particular equation here will satisfy calculations for Jacobian for the bottom, because I can take partial derivative of y in respect to u and get 3/10, and partial derivative of y in respect to v and get negative 1/10. So that's cool. Now I have to do this one more time to fish out the x equation out of this mess. And we get that by solving for y and plugging it in there, and then that fish outs the other one. So now, for the second one, let's do this maybe dark blue or something. So for the second one, I solve for y, so 4y is equal to u minus x. So y is equal to 1/4 u minus 1/4 x, and now we have to plug that in, and it's not going to be too much fun. So v equals 3x plus 2 times this is now 1/2 u minus 1/2 x. And I put x's on a pile, so that's 5/2 x plus 1/2 u. And you can multiply everything by 2 to get your 2v is equal to 5x plus u. And you just solve for 5x now. So 5x is going to be 2v minus u. And finally, x equation from here is 2/5 v minus 1/5 u. There's the transformation, finally. So what used to be given to us, straightforward, now we have to actually do some work to get. And that's problem 26. So now what I'm going to do is I'm going to compute the Jacobian of uv, which is again partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. Now all of these are just going to be fractions real quick. So partial x of u is negative 1/5. Partial x of v is 2/5. Partial y of u is 3/10. And partial y of v is negative 1/10. I hope you remember the way to solve the determinant for 2 by 2, because that has been ancient history, exactly. So we go that way. So what I have is negative 1/5 times negative 1/10 plus, no, minus, sorry, 3/10 times 2/5. And I understand that I can cancel 2 and 10, but I'm not going to do that because when I multiply this, I already have common denominator, and I don't have to suffer with that, at least. So this is going to be 1 over 50 on the first one, minus 6 over 50, which gives you negative 5 over 50, which gives you negative 1 over 10. So your Jacobian, in this particular case, turned out to be negative 1 over 10. It depends on functions. Do you have to have a number there? No, could be a function in terms of u and v. The Jacobian notation clearly suggests that your answer could be a function of u and v. It depends on your transformation. Because if your transformation is what we have so far, which is just linear stuff, clearly these numbers are constants. So you're getting a number at the end. But if any of these puppies over here in transformation is e to the x or a cosine or x squared, right? Well, u squared, then these turn out to be functions in terms of u and v, and you have to, use appropriate algebra to get whatever is on the other end. And that thing could be anything. So we have all of the building blocks to put this thing together. Yes?
What is negative 1/10? Like, what does that mean?
Okay. I will explain that as soon as I put the whole formula together. It definitely has purpose and meaning. So yeah. What do you mean no coffee? This is not. It's not the same rules for all of us over here. What the hell? No, I'm just saying. I'm just saying. Shush. You show me last time you see a cop drive the speed limit. So yeah, exactly. So when I say no coughing, I mean no coughing, and you don't get to say it. So exactly.
You got a good point.
All right. We will never be equal. That's the moral of the story. All right. So let's go and take a look at the transformation formula for 2D. And then we're just going to write the same thing later for 3D as it emerges. So, the integral you want to transform, double integral in x and y, dA, will become double integral over the transformed region S. Your function will now be transformed through u and v as well, times the Jacobian of u and v, and absolute value times dA. So this is your formula. Now you're looking at this and you're probably going, what the hell, right? You remember the u sub part? For u sub, we had to transform the function, and we had to transform the du, right? dx into du. That's what your Jacobian is. That transformation. So, the first example I did over here, right there. You see how this 1/2 pops out of nowhere? There was no 1/2 in original problem, and all of a sudden there is 1/2. There is this 2x business over here in front of the dx to create du. right? That's what a Jacobian is. This is Jacobian for 1D case because you have the transformation of dx into du. And what is your Jacobian? So all the partial derivatives between x's and u's and y's and u's and v's, right? So that's that purpose. I mean, you know, to annoy you, it's only 10%. 90% is obviously its true use. So Jacobian has to be computed. So now we can finally do the whole problem. We can do the whole thing now. Let's write the process. Number 1, transform the region. Number 2, get Jacobian. Number 3, put the new integral together. Number 4, integrate. Number 5, win/celebrate. There you go. You should do this, right? Because when you accomplish one of these problems, it's always a little victory in itself. So let's find a problem. Right, who is in class today is usually not in class. Because my allergies are kicking in, and you should leave.
I'm always here then.
We did the transformation already for problem 28, so I will just steal the transformation and proceed with the Jacobian, putting the integral together and integrating. So problem 28. You also have problems 29 and problems 30 transformed, so you should follow up for homework. I understand you do your stuff online, yeah, fine, but you already have regions transformed for these two in notes, so complete those problems all the way through. So I'm going back to problem 28, which was region R, x squared y dA, with the region, and I say transformation done, and then I'm going to look for the transformation. That's 26, that's 30, that's 29, 28, good. So we have the nice beautiful square. Okay, so transformation is done. So I'm just going to say, okay, stealing that. This is region S now for U and a V. And these are ones. So 1, 1 over there and 0, 0. And our transformation for this one, because we need for Jacobian, is x equals 2u. And y equals 4v plus 2u. So what should I do?
4b?
4v, yes. So step 1 is done. Step 2, Jacobian UV is partial x, partial u, that's 2. Partial x, partial v is 0. Partial y, partial u is 2. Partial y, partial v is 4. So the whole thing is 8. Let me label. So this is step 1. This is step 2. Step 3. Put the integral together. Integral over region S. Instead of x, I have to put 2u squared. Instead of y, I have to put 4v plus 2u. Times the Jacobian, 8. And then du, dv, or dv, du, it doesn't matter because it's a square. So it's 0 to 1, 0 to 1. Step 4, integrate. Now, before I go there, I just want to make sure that you guys understand this. So here comes the green color over here. This puppy over here is your x squared. This puppy over here is your y. This one over here is your Jacobian, UV. And this is over here your dA. As you are following your formula listed up there in red. See that thing? It looks so crazy. Not a problem at all. This mess over here tells you to take the old function you have, replace every x with whatever those are with u and v, replace every y with whatever those are, because this is f of x, y. So every x is replaced with a function of u and v, and in our case with just 2u. And every y is replaced with a function of whatever the hell it was, 2v minus 4u or whatever. So that's what I got at the end. That's a little bit too much. There we go. Number 4, solve. First we have to multiply everything. Observe that I have 2 squared times a, that's 32 in front of the integral. And now I have u squared multiplying the entire, oh, I can actually put 64 in front, because I can factor out 2 from the y parenthesis. Alright, so this is out. I have vu squared plus, no, 2vu squared, and then u squared u cubed, du dv. When I multiply everything out. So if you didn't follow that, you should have. 2 squared is 4. I factor 2 from here. That makes it 8. 8 times 8 is 64 in front of the integral. So all of the constants are kicked outside. What's left? U squared times 2v. U squared times 2v. And u squared times u, which is u cubed. All the constants of 2 is factored out. So this is 2, this is nothing now. And that's why there's no constant there. And that's just cleaning it up. And I love the fact that I just spent like 2-3 minutes on explaining the algebra and factoring, where now for integration I just say, just plow through it, because you're all able to integrate. You're not able to add exponents. That's that's always the issue, right? So we are going to integrate in terms of u first. Should have done dv du, but that's okay. We have 2/3 vu cubed plus u to the 4 over 4, computed from 0 to 1, and we still have dv. That's 64 integral 0 to 1. When I plug in 1 for u, I get 2/3 v plus 1/4 everything dv. And now 64 times the integral of this is v squared over 2. 2 and 2 cancel, so I have v squared over 3 plus 1/4 v from 0 to 1, and that's 64 times 1/3 plus 1/4. And you get 64 over 3. No, let's just do the 7/12. So 64 times 7 over 12. Divide by 4. So that's 16, right? Times 7 over 3. 70. 112 over 3. And there it is. We were looking for the volume of the object because we have a 2D integral and we had the function inside. So the double integral gives us the area of the base. The function on top gives us some kind of the top, and base times the lift that we get from our, we were looking for volume. Now it wasn't pleasant, that integral wasn't pleasant, so we transformed it from parallelogram base into a square base, and then we use this so to get. So if you are to solve over the parallelogram base with more effort, your answer for this has to be 112 over 3 as well. Presuming that all of our calculations are correct. It's like a blanket or something. Now, since we are here, the next problem is obviously 29. Do that one quick. And then move to the 3D, because we can. So transformation is x equals to 2u and y equals to v minus u. We just did the transformation for this. I am going to go back and steal that transformation for problem 29, and it's this little beautiful triangle over here, right? So region S, same problem, we just need to do integration now in Jacobian and all that stuff. So problem 29, I already had the transformation done before, right?
So we didn't do. We never had the squared.
I know you didn't need that. You just needed the limits, which I gave you the region R, and I gave you transformation. Now I'm giving the rest of the problem, so we can do the stuff. Every transformation, guys, that's just like a warm-up, and then you go into the Jacobian, which is always, right? Then you put the integral, and then you have the afterburner which is solving the integral, and yeah. So Jacobian. So step number 1, I'll just say done above. Step number 2, then later on step number 3 to put the integral together. So now what I have is a Jacobian over here. Partial x partial u is 2, partial x partial v is 0, partial y partial u is -1, partial y partial v is 1. Jacobian is 2. You just have to memorize the formula for Jacobian, and everything goes smoothly after that. We have a double integral over this new region, and look at that. Now we have to replace all of these things with our substitutions. So x squared becomes 4u squared, and then the square root, x is 2u plus 2 times, and y is v minus u. And we have times the Jacobian, which is 2. And now we have dv du or du dv. Well, hopefully it's going to be dv du. And now when you, so y, because your representative rectangle du should be in charge, because that's the one that it's like dx, right? And it's the outer integral sweeps from 0 to 1, and the inner integral sweeps from 0 to the function 1 minus u, or negative u plus 1, whatever. You see there is a y-intercept of 1, and it goes as a linear negative, right? So all we need to do is to solve this kick 8 outside of the integral. Double integral, and clear as much algebra as you can. So we have u squared square root. Now guys, when you distribute the 2, you will get negative 2u, right? So it's just the square root of 2v. 2 is kicked outside already, and I just have a dv du. Like this. 1 minus u. It's the top formula over here. It's 1 minus u. When you are doing the algebra, you have the line that goes through 1. That's your y-intercept. So you would say mx plus b, right? mx plus b. So your b is 1. So you have plus 1 there. You know you're going to have x, and now you need the slope. The slope is 1 unit down, so that's negative 1. 1 unit over positive 1. Or you can pick your 2 points. You have them, 1, 0, 0, 1, and then run your algebra between those 2 points to find the slope, to find the b, like whatever needs to be done. Yes.
It's also possible to do dv.
Yes, it is. Yeah. I mean, at this point, you shouldn't do it, but at this point, you can just regard the new transformation as, again, x, y, and then you just recycle. But it would collide with the old notation and things like that, because for this transformation, since we already suffered to transform the region, we do not go back in original variables to compute with old limits. It doesn't happen. We transform everything. We transform the region, we transform the function, and we also transform the dx, dy, or dA, and Jacobian is part of that transformation, right? So it's Yeah, that's that. So now we have to integrate. I am going to kick square root of 2 outside as well. So we have 8 root 2, double integral 0, 0, 1, 1 minus u squared, square root of v. I'll put that as v to 1 half, dv du, and then now just integrate. 8 root 2 integral 0 to 1, and now u squared is the constant, v becomes v to the 3 halves over 3, and then 2 goes on top, from 0 to 1 minus u, and we still have du to worry about later. Kick 2/3 outside because we don't need that, so that's a 16 root 2 over 3. Integral 0 to 1. We have the u square, and now you have the parenthesis 1 minus u to the 3 halves over here, du. And now how's your calculus 1 doing? So what should we do with this now? How do I integrate this? How do I integrate this? Or we just say, such is life, and move over. Move from alpha will work, yeah. How do we integrate this? Integration by parts, exactly. Because you gotta get rid of u squared. Well, what are you gonna do with it? Right? You can't use trig sub because this is not u squared. It was u squared and it's a trig sub. It's easy. So integration by parts. I told you that these problems are great for killing time and carpal tunnel, right? It's amazing what these things do for you. So integration by parts. There you go. What are you gonna do when you go home? Obviously this, right? Losers are gonna go and watch Bachelor and other nonsense. You guys, integration by parts. That's the right. Alright, so it's all fun and games until you run into the 3x3 case, right? In which case all of this becomes exponentially worse because your Jacobian now is 3x3. That's 9 entries, and it's more work. So what is the formula for 3x3 Jacob? Why? Oh, class ends at 7:35. So this is a late class, late start class. Oh no, wait, that's my Calc 1 is the late start. This is a regular. 7:20? There's no way we can squeeze in an example. I'll try. 3D. So your triple integral now over region D of a function f, x, y, z, conserve space. Turn your notebook sideways, like you have it. Oh no, your paper is still there. Okay. It's the triple integral over transformed region S, f of g u v w comma HUVW, comma PUVW times the Jacobian UVW dV. Fits. Nice. This should be the next thing you write on a napkin when you go outside. You ask the bartender for another napkin and a little bit of tape to put it together. Okay. We have a casualty. Oh no, he's good. Okay. For the moment, I thought checked out.
6 a.m.
Casualty of. All right. So what's our Jacobian of UVW? It's gonna be busy. So it goes first row dx, second row dy, third row dz. So partial x, partial u, partial x, partial v, partial x, partial w. Next row. Partial y, partial u, partial y, partial v, partial y, partial w. Next row. Partial z, partial u, partial z, partial v, partial z, partial w. There's your Jacobian. So first row x UVW, second row y UVW, third row z UVW. And that goes there. All right, let's see if we can do anything with this stuff. $42. We have a triple integral d dv. At least we don't have to worry about the function inside. Bounded by planes y minus 2x equals 0. Y minus 2x equals 1. Z minus 3y. Z minus 3y equals 0. Z minus 3y equal 1. Z minus 4x equals 0. Z minus 4x equals 3. Good. Yeah, that's that. Now, if you look at this, you are going to see 3 pairs of parallel planes. So it's not a problem. If you look at those 2 walls, they are parallel, and only one variable will be determining the space difference between those 2 walls. There's the one that we stand on and the one above our heads. If this one is equal 0 and this is equal to 10, right? They have the same structure before equal to a number on the other side, and same goes to the wall behind you and the wall for the whiteboard. So what is this? This is going to be some kind of, so think of it as a box that you kind of shear to the side. It's leaning, right? That's what it is. And you have the top and bottom parallel. They're not on top of each other, they're like this, and then the rest of the problem goes that way. So you have these sides parallel, these sides parallel, and these sides parallel, even though they're not on top of each other. And then we want to change that into something that works well. So they never gave us transformation for this in a problem. So you have to figure out the transformation on your own. Right? So you're looking at this thing and you go, like really, the U and a V thing? Yeah, the U and a V thing. But then you quickly realize that these things are given to you as pairs. So there is nothing that stops you from calling this a U. And if this is called a U, then U equals 0, U equal 1, and then V equals 0, V equal 1, and W equals 0, W equal 3. You're getting a box. You see that? So it's not as difficult as you think. It could be, but it's not. So the transformation I want to use is U equals 0 and U equals 1 from that pair, and V equals 0 and V equal 1 from this pair, and W equals 0, W equals 3 from the last pair. And I'm going to actually box them off as pairs, so you know what we're talking about. I'm just going to switch this into blue today, please. Thank you. Now, when I do that, what was my transformation which made this possible? Transformation is y minus 2x equals u, and z minus 3y equals v, and z minus 4x equals to w. So that was my transformation. I came up with this transformation because everything was parallel. I had 3 parallel plates, so it's just, I guess, natural. I don't know. Great. So I have that now. Remember how the Jacobian is dx du? So we have to flip all of these equations now, because they need to be x equals, in terms of x, y, w, y equals x, right? And the fastest way to do this is to actually maybe use the matrix, row reduced echelon form, things like that from linear algebra. You don't have them available to you, unfortunately. So let's dance around these equations, see what we can get. Congratulations. I switched to that. So what should I do? So this is the fun part now. So y minus 2x equals u. Aha. Let's write them as the system of equations. So negative 2x plus y space for z equals u. And then the next one is negative 3y plus z equals v. And the last one is negative 4x space for y plus z equals to w. Alright, so if I subtract these two equations, I will kill a z. So by subtracting these two equations, I go top minus bottom. So I get 4x minus 3y equals to v minus w. And I also have negative 2x plus y equal u. Top equation times 2 and then add them. Top equation times 2, that's a negative 4 that dies. This is negative y equals to 2u plus v minus w. And here is your transformation for y. Y equals negative 2u negative v plus w. That's one of them. Rinse and repeat for others. So what else can I do from the same set? I can do top times 3. So negative 2x plus y equals u, and 4x minus 3y equals v minus w. I can do top times 3 plus the second equation. And if I do that, top times 3 becomes negative, gives me negative x over here, negative 2x. Y's die, and I have 3u plus v minus w. So let's see one more time. 3 times this is negative 6 plus 4 is negative 2x. These die, 3u plus v minus w. Great. So I have x equation from here. And that one divides through by negative 2. So I have negative 3 halves u minus 1 half v plus 1 half w. And that's the second equation. Now to get this equation, you can simply, dare I say, plug everything into, let's say, the third equation. You plug in x in the third equation. So from here and here at the same time, I have negative 4 times negative 3 halves u minus 1 half v plus 1 half w is plus z is equal to w. And you see that z is the only unknown. So just solve for z. Well, distribute negative 4 first. It becomes positive 6u plus 2v minus 2w plus z equals w. So z equation is negative 6u negative 2v and positive 3w. Nice. So now we have our region. in our 3D realm over here. Let's go with the realm this way. U, V, W. I go 1 unit each. And then 3 units up. So 1, 1. This is just a box. This is my region S. So I got that transformation by just looking at those pairs up there. So what should I do now? Well, step number 2, compute the Jacobian. Jacobian of UVW is equal to partial x partial u negative 2. Partial x partial v negative 1. Partial x partial w. Oh no, that's not x. Partial x partial negative 3 halves. Partial negative 1 half. Positive 1 half. Negative 2, negative 1, 1, negative 6, negative 2, and 3. And there you go. What happened? You remember the IJK cross product 2 vectors for yeah, same way. So we have negative 3 halves times the determinant of this thing over here. That's negative 3 plus 2, negative 1. And then minus negative 1 half times the... So when we do negative 1 half, we have to use this and this. So that's negative 6 plus 6, that's a 0. And then finally plus 1 half. If I'm using 1 half, I have to use these puppies here. So that's 4 minus 6 is negative 2. Nice. So let's say this is good. The same way we did the IJK. You multiply I with this. But now it's not I, it's a constant. So you have to put, instead of I, you put the number. So it's the same thing as when you're looking for a plane, having the two lines, 2 vectors. So now this is 3 halves, is dies, minus 1, 1 half. The old Jacobian is 1 half. So luckily our integral is easy. We don't have anything to transform inside, so we can just go dw, dy, no, dv, du. I forgot my 1 half from the Jacobian. That has to be in there. 0, 0, 0. Du is 1, dv is 1, and this one is 3. So when you solve this integral, it's clearly 3 halves. Triple integral. Gotta learn how to compute those things. Ta-da! Look at that. 4 minutes to spare. We can do another example. Or you can just leave, but another example would be better. That's change of variables in 2 and 3D, and technically with everything else, it's just good luck, right? It's a lot of practice, a lot of work. It is not as straightforward as U sub is, but again, it's, you know, stuff that you actually learn as you practice. So, you know, with practice you will get faster and better, and, you know, try not to take an hour and 20 minutes to do this problem on a test and then have zero time for, you know, other problems. The next exam, due to length of these problems, is anywhere from 6 to 7, maybe 8 problems. We can't really have, you know, 10 problems plus a replacement. That's 11. Or we could, but then the exam is 2 hours, but then that's like your final, and yeah, it could be like a final. So these problems are very lengthy, and right, I mean, I think most of the 2Ds that we did were more work than actually this 3D, but again, this is the, you know, biggest joke of a 3D problem that you can get. So you just had these parallel planes, and right. Maybe it would be beneficial for all of you to take a look at the problem 44, which is ellipsoid. They give you the transformation to use, and I can guarantee that that transformation is going to turn the ellipsoid into a sphere, and then you can use your spherical integrals to win, right? So there is a lot of good stuff that you can practice here for this to work out. So that's 13.7. That's chapter 13. Hope you're not disappointed. I will see you all Monday for chapter 14. Bye.